For over 3 decades, astronomers have tracked a massive, unexplained heat signature glowing at the center of nearly every active galaxy. This excess infrared emission was a constant feature in archival surveys, yet it consistently defied standard models of how a black hole consumes matter. The prevailing consensus offered a highly logical explanation. It was exhaust. Astrophysicists concluded that intense radiation from the central engine was blasting surrounding hot dust outward, creating massive, glowing polar outflows that produced the excess light. But in January 2026, the James Webb Space Telescope targeted the Circinus Galaxy and proved that assumption was fundamentally backwards. The glowing dust isn't being expelled. The vast majority of it is actively being eaten. To understand how galaxies evolve, we first have to track exactly where their central supermassive black holes are dumping heat. If we misidentify the structural source of that thermal energy, we misunderstand the entire thermodynamic engine of the galaxy.
In an active galactic nucleus, the immediate environment around the black hole is shrouded in a thick, donut-shaped ring of densely packed gas and dust, known as the torus. Before any material actually crosses the event horizon, intense friction and immense gravitational forces heat this feeding ring to extreme temperatures. This superheated dust absorbs higher energy radiation from the inner accretion disk and re-emits it as a blinding mid-infrared glow. Throughout the 1990s and early 2000s, space-based observatories could easily measure the immense total volume of this thermal energy. However, they completely lacked the spatial resolution required to pinpoint its exact physical geometry. Because the optical data was merged into a single, unresolved blur, researchers had to rely heavily on spectral energy distribution models. Without a clean structural map, it was mathematically easier to attribute the brightest infrared signals to the expanding exhaust plumes, rather than to a tightly bound feeding ring. That entire paradigm changed with the publication of a January 2026 study in Nature Communications.
Using Webb's highly specialized NIRISS instrument, an international research team secured a direct spatial measurement of the feeding zone at the core of the Circinus Galaxy, effectively isolating the true origins of the thermal radiation. The observational data from Webb is definitive. The researchers proved that exactly 87% of the excess infrared emission in the Circinus core comes directly from the dense, incredibly compact torus. It is structurally the dominant thermal engine of the central galactic environment, far outshining the surrounding material. In stark contrast, the data revealed that less than 1% of the emission is actually generated by the hot, dusty outflows. The pre-2026 standard models had confidently assigned the bulk of the thermal signature to those massive polar cones. Webb's high-contrast imaging proved the exhaust is barely contributing to the overall infrared glow. It is critical to note that Webb did not image the event horizon itself. Black holes emit no light. Instead, the telescope successfully isolated the 33 light-year-wide feeding zone, proving that the energetic environment immediately surrounding the abyss is dictated primarily by consumption, not expulsion. Webb definitively flipped the script on this moderately bright Seyfert galaxy. But to appreciate why this specific measurement required a massive leap in optical engineering, we have to look closely at the exact physical scale of what the telescope actually had to capture. The target of the breakthrough January 2026 observation was the Circinus Galaxy. Located roughly 13 million light-years from Earth, it serves as one of our most critical local laboratories for studying active galactic nuclei. By cosmological standards, 13 million light-years is practically next door, making Circinus a prime candidate for detailed structural imaging. But in astrophysics, nearby does not guarantee clarity. At the core of Circinus lies a moderately bright supermassive black hole, spectroscopically classified as a Seyfert nucleus. The environment immediately surrounding this central engine is deeply enshrouded in matter. High-energy ultraviolet and X-ray photons continuously pour out from the inner accretion disk. This intense radiation slams into the surrounding walls of dense gas and dust, heavily heating the material before it ever crosses the event horizon. Because the dust absorbs these higher energy X-rays, it re-emits that stolen energy in the infrared spectrum. This creates the overwhelmingly bright thermal signature that astronomers have tracked for decades. Webb wasn't looking for the black hole itself, which emits zero light. What it saw was in fact a quite different structure entirely. This massive crown shroud of sulfur and phosphorus radiation is only to be seen in infrared.
Instead, the team needed to map the exact geometry of this surrounding hot dust to see where the energy was actually pooling. When the James Webb Space Telescope locked its interferometry instruments onto the galactic core, it finally mapped the specific structure of this feeding zone. Direct spatial measurements isolated a dense, donut-shaped ring of material known as the dusty torus. The data revealed that this primary fuel reservoir is remarkably compact, measuring roughly 33 light-years across. To put that physical scale into perspective, the entire host galaxy spans tens of thousands of light-years. The torus itself is merely a microscopic speck at the exact gravitational center. A 33 light-year object, viewed from a distance of 13 million light-years, is vanishingly small in the night sky. While the precise internal clumpiness of this dust is still constrained by mathematical modeling, its overall diameter is now a hard observational fact. This extreme scale differential defines the entire 30-year mystery.
Trying to observe the torus from Earth is the geometric equivalent of trying to measure a glowing grain of sand from miles away, all while a spotlight is shining directly into the telescope lens. Because the structure is so tiny, earlier infrared observatories had no choice but to treat the entire galactic core as a single, unresolved point source of light. They physically could not distinguish a compact feeding ring from a massive, sprawling cloud of expelled matter. At that immense distance, resolving a 33 light-year structure is near the absolute limit of modern optical engineering, which is exactly why a previous generation of astronomers spent decades relying on a mathematically rigorous, yet structurally flawed picture of cosmic exhaust.
To see why Webb's recent observation is such a paradigm shift, we first have to understand the physics that governed astrophysics for decades. The outflow model was not a blind guess. It was the most logical consequence of fluid dynamics and radiation physics applied to an active galactic nucleus. If you have an incredibly hot accretion disk generating immense energy, that thermal energy has to go somewhere. The dominant physical force at play here is radiation pressure. The high-energy photons emitted from the intense friction of the inner accretion disk carry actual physical momentum. When a supermassive black hole is actively feeding, the sheer volume of ultraviolet and X-ray light radiating outward becomes extreme. It is so powerful that it can overcome the gravitational pull of the central mass, physically pushing surrounding gas and dust outward into deep space. This escaping kinetic energy naturally follows the path of least resistance. Because the equatorial plane of the black hole is blocked by a dense ring of infalling matter, the radiation blasts outward through the poles. Pre-2026 models mapped these dynamics mathematically and concluded that this radiation pressure was ejecting massive quantities of hot dust outward, creating gigantic, glowing exhaust plumes. For nearly 30 years, these superheated streams of expelled matter, often referred to as polar outflows, were the standard astrophysical explanation for the infrared anomaly.
Astronomers relied heavily on spectral energy distribution models, or SEDs, which measure the total output of light across various wavelengths. Because they could not physically resolve the geometry of the dust, the mathematical profile of massive, glowing exhaust plumes provided a nearly perfect fit for the archival data. There was always an alternative explanation, that the torus of material feeding the black hole was simply much thicker and hotter than expected. But the math of the outflow model was incredibly persuasive. In theoretical simulations, radiation pressure effortlessly explained both the scale of the thermal emissions and the physics of how a galactic core regulates its own temperature. It is also crucial to note that these historical models were not entirely wrong about the physics.
Outflows absolutely exist, and they remain a real physical consequence of active accretion. Superheated streams of exhaust are actively being blasted into space by these central engines. The error was not in the existence of the outflows, but in their assumed dominance over the total infrared signature. The scientific consensus leaned heavily toward the outflow theory, primarily because researchers had no technological way to definitively prove otherwise. Their theoretical models were highly dependent on indirect spectroscopy, rather than direct, high-contrast spatial imaging of the dust structures themselves. Astronomers were essentially forced to reconstruct the geometry of a galactic core strictly from its thermal footprint, measuring total heat without knowing exactly which structure was burning. To definitively prove whether the light was coming from the compact feeding ring or the massive exhaust plumes, astronomers needed to map the heat directly. But they were trapped by a fundamental limit of optics. The outflow model harbored a fatal flaw, but it was perfectly hidden inside a blur of blinding starlight.
What exactly happens when you try to take a picture of a structure this bright? When you try to photograph the immediate environment of an active supermassive black hole, you run into a fundamental barrier in optical physics. The central engine and its densely packed nuclear star clusters are blindingly bright. As that intense, concentrated light strikes a telescope's optics, it inevitably diffracts and scatters, bleeding outward across the sensor and creating a massive halo of glare. Older space observatories, like the Spitzer Space Telescope, were remarkably sensitive to this infrared light, but they were severely limited by their spatial resolution. They could accurately measure the total, aggregate amount of thermal energy pouring out of the Circinus core, confirming that massive amounts of hot dust were present. But they simply could not map the exact geometry generating that heat. Because of this hard diffraction limit, compact structures located just a few dozen light years from the black hole were completely swallowed by the central glare. Without the raw resolving power to visually separate the tightly bound feeding ring from the vast expulsion zones, the torus and the outflows occupied the exact same blurred pixels on the telescope's detector.
To astronomers analyzing this unresolved data, the galactic core appeared as a single bloated artifact, a blurry blob of excess infrared energy. Since the distinct physical structures were completely indistinguishable from one another, researchers were forced to rely on indirect spectral measurements and theoretical physics to explain the heat source. Because radiation pressure from the accretion disk is a universally recognized force, modeling the blur as a massive, glowing exhaust plume remained the most scientifically rigorous conclusion available. Ground-based observatories couldn't pierce this glare either. Astronomers deployed advanced adaptive optics to mechanically deform mirrors in real time, attempting to cancel out the blur caused by Earth's atmosphere. But while this helped in the near-infrared, the inherent thermal noise of the atmosphere itself overwhelmed the delicate mid-infrared signals required to map the dust around extragalactic targets. The challenge was ultimately a severe signal-to-noise barrier. The faint thermal signature of a tight 33 light-year dust ring
was entirely drowned out by the overwhelming noise of the active galactic nucleus. The previous consensus survived for 3 decades, not because astronomers were poor theoreticians, but because no instrument in existence could sharpen the image enough to physically isolate the different structural components of the core. To solve this 30-year anomaly, astronomers realized they couldn't just rely on brute force magnification or launch a marginally larger primary mirror. They needed a highly specialized mechanism to physically block the blinding starlight contaminating the observation, allowing the faint, closely bound dust structures to finally emerge from the glare. They needed a way to isolate the interference patterns of the light itself. This meant pushing the resolving power of a space observatory far beyond its standard physical limits, entering a regime of high contrast imaging never before attempted on a distant galaxy. How did the James Webb Space Telescope trick its own hardware into performing like a massive 13-meter lens to finally separate the food from the exhaust? In January 2026, an international research team led by Enrique Lopez Rodriguez published a breakthrough study in the journal Nature Communications that completely bypassed the optical limits of standard space photography. To pierce the glare of the Circinus Galaxy, they deployed a rarely used, specialized piece of hardware aboard the James Webb Space Telescope. Housed inside Webb's near-infrared imager and slitless spectrograph, known as NIRISS, is a physical shield called an Aperture Masking Interferometer. When commanded, this mask drops into the optical path, deliberately blocking out the vast majority of the light gathered by Webb's massive golden mirrors. It leaves only 7 specific, mathematically spaced hexagonal holes open to the incoming photons. Counterintuitively, throwing away most of the starlight is exactly what allows the instrument to achieve unprecedented sharpness. By forcing the remaining light streams to cross and interact, the mask generates a highly precise interference pattern. This carefully engineered interference pattern mathematically cancels out the overwhelming, blinding glare of the surrounding nuclear star cluster. More importantly, it artificially doubles Webb's maximum standard resolution. For this specific observation, the mask tricked the telescope's optics into mimicking the resolving power of a massive 13-meter space observatory. Capturing this data marked a critical historical milestone in astrophysics, representing the first time high-contrast interferometry was ever successfully executed from space against an extragalactic target. By decoding the resulting interference fringes, the researchers finally separated the blurry, blown-out core into distinct structural components. The data immediately overturned the prevailing baseline models. Webb proved that a staggering 87% of the mysterious excess infrared emission in the Circinus core comes directly from a dense, donut-shaped dust ring, roughly 33 light-years across. This is the torus, the immediate feeding zone where intense radiation and physical friction superheat the tightly packed gas and dust just before it crosses the event horizon. The competing theoretical structure, the massive, violently expelled polar outflows, accounted for less than 1% of the total mid-infrared thermal signature. For 30 years, standard spectral energy distribution models had assumed those hot, dusty exhaust plumes were the dominant source of the glowing anomaly. The January 2026 data definitively proves those assumptions were inverted. In the Circinus Galaxy, the glowing dust is not being blasted outward as cosmic exhaust. The overwhelming majority of it is actively being eaten. This single observation permanently altered the baseline assumptions for modeling active galactic nuclei. Webb's hardware successfully solved the anomaly by structurally mapping the heat, entirely redefining how we understand the immediate environments of moderately bright Seyfert galaxies. The feeding ring is the undisputed dominant thermal engine in this local laboratory, efficiently converting gravitational friction into an overwhelming infrared beacon. But fixing the mathematical model for Circinus immediately triggers a much larger, more violent problem for astrophysicists. The dynamics of a black hole are highly dependent on the energy scale of the specific object being measured. Does this feeding ring dominance hold true universally? Or does the physical geometry completely fracture when a much larger supermassive black hole is feeding and spinning at the absolute maximum limits of gravity?
To answer that, we have to look closely at the exact wording in the 2026 Nature Communications paper. Lead author Enrique Lopez Rodriguez and his team were very careful to attach a specific scientific caveat to their breakthrough. The Circinus Galaxy is officially classified as a Seyfert, meaning its central accretion disk is only moderately bright. As definitive as the new data is, the researchers explicitly warn against assuming that this single structural map perfectly rewrites the rules for every active galactic nucleus in the universe. The physical mechanics governing a moderately feeding black hole do not necessarily scale linearly to the most violent engines in the cosmos. Consider a distant hyperluminous quasar. In these extreme environments, the supermassive black hole is consuming matter so rapidly that the sheer friction of the accretion disk generates an overwhelming amount of high-energy light. This introduces a critical astrophysical threshold known as the Eddington limit, the exact point where the outward push of radiation pressure actively challenges the inward pull of gravity.
When a quasar approaches the Eddington limit, the outgoing photons exert tremendous physical force on any surrounding material. In a moderately bright system like the Circinus Galaxy, the black hole's gravity is clearly winning the tug of war. This gravitational dominance allows the infalling dust to neatly settle into that brilliantly glowing 33 light-year wide feeding ring we now know dominates the infrared spectrum. But the thermodynamic environment around a hyperactive quasar is operating under entirely different constraints. In those highly active systems, the radiation pressure is vastly stronger, effectively acting as a cosmic wind. It is entirely possible that the outward blast of light simply overpowers the gravitational pull, forcibly expelling massive amounts of hot dust into deep space before it ever has a chance to settle into the central torus. Because of this extreme dynamic, it remains a fully open hypothesis in modern astrophysics whether the old exhaust model might actually still be accurate for quasars.
If the radiation pressure successfully blows the dust apart, those superheated outflows could still be the dominant source of the excess infrared emission in high luminosity targets. The 87% torus dominance established in the Circinus observation might fracture entirely when applied to a larger, hungrier black hole. Alternatively, some researchers argue that a quasar's torus might just scale up in thickness and density, acting as a massive shield that withstands the barrage of light and continues to dominate the thermal signature. Currently, we simply lack the high-resolution aperture masking interferometry data on those distant hyperluminous targets to confirm exactly how their dust structures behave. The fundamental physics of radiation competing against gravity applies universally, but we do not yet have the spatial resolution to prove which force wins at the absolute extremes of the mass scale. We know the old consensus is dead for Seyfert galaxies, but the quasar debate remains completely unresolved. This balance between food and exhaust clearly shifts depending on the size and appetite of the central engine.
But tracking this exact structural ratio, figuring out definitively how much hot dust is eaten versus how much is blasted away, isn't just an exercise in cosmic accounting. The thermal energy expanding outward from this boundary zone acts as the primary thermodynamic engine for the entire star system. And whether a supermassive black hole is primarily feeding or spitting has direct, irreversible consequences for its host galaxy. To understand why astronomers care so deeply about this structural ratio, we have to look past the mere accounting of infrared light and look at the sheer mechanical force involved. The environment immediately surrounding a supermassive black hole is the dominant thermodynamic engine in any active galaxy. Whether that engine is primarily expelling matter or quietly consuming it determines exactly how much kinetic energy escapes into the broader galactic disk. This energy transfer is known as active galactic nucleus, or AGN, feedback. As the central black hole feeds, it pumps heat, radiation, and physical momentum back into its host environment. But the exact pathway that energy takes matters entirely. If the heat is just tightly bound inside a dense feeding ring, the energy remains highly localized. If it's blasting outward as massive exhaust plumes, that kinetic energy physically slams into the wider galaxy. When those superheated outflows are powerful enough, they act like a cosmic snowplow. They ram into the galaxy's cold, molecular gas clouds, the exact material required to form new stars.
If the exhaust is violent enough, it will heat up or physically clear out that star-forming gas entirely. Astrophysicists call this destructive process quenching. Once the gas is gone, the galaxy simply stops creating new stars and effectively begins to die. But AGN feedback isn't always a shutoff valve. Under different thermal profiles, the shock waves expanding from the core don't expel the gas, but rather compress it. That sudden compression forces the molecular clouds to collapse under their own gravity, triggering sudden, massive bursts of new star formation. So, the exact ratio of consumed versus expelled matter at the core literally dictates whether the galaxy will bloom or go completely dark. For decades, our mathematical frameworks for galactic evolution were built on the assumption that moderately bright active galaxies were aggressively venting hot dust outward. We modeled their life cycles assuming this exhaust was constantly shaping the inner stars. But Webb's January 2026 data proved that in these moderate environments, the vast majority of that energy is actually locked up in the torus, forcing us to recalculate how these specific galaxies regulate themselves.
Of course, thermal outflows aren't the only forces at play here. Relativistic jets and magnetic field winding also play massive roles in how a black hole communicates with its host galaxy, alongside the heat. But the thermal energy budget remains a primary piece of the puzzle. If astronomers miscalculate how much heat is escaping the core, our models for how a galaxy will evolve over the next billion years will just be fundamentally wrong. If we want to accurately predict whether a distant galaxy is preparing to ignite with new stars or shut down its stellar factories forever, we have to know its exact torus-to-outflow ratio. The Circinus observation proved that Webb has the optical engineering required to map that ratio directly, without relying on blurry guesswork. The tool works. Now we just have to point it at the right targets. We know how the thermal engine operates in moderately feeding black holes. But to finalize the rulebook of galactic evolution, we need to push this exact same interferometry mask to its absolute limits, aiming it directly at the most violent, hyperluminous objects in the cosmos.
The January 2026 Circinus observation permanently altered the baseline models for moderately active black holes, proving that Webb's Aperture Masking Interferometer can successfully isolate a 33 light-year core. But Circinus was only a proving ground. To truly finalize the rulebook of galactic evolution, astronomers are preparing to aim this exact same optical trick at the most violent environments in the universe, high-luminosity quasars.
When a supermassive black hole feeds at the Eddington limit, the outgoing radiation pressure becomes so intense it physically resists the inward pull of gravity. In these hyperluminous environments, researchers hypothesize that massive amounts of dust are forcibly expelled before they can ever settle into a stable torus. Testing this requires targeting quasars deep in the high redshift universe, observing them during their most active, chaotic periods of growth. Deploying the interferometry mask against these distant giants introduces a severe engineering constraint. High redshift quasars are dramatically further away than the relatively local Circinus Galaxy.
Because the mask physically blocks most of Webb's primary mirror to create its high contrast interference pattern, it drastically reduces the total number of photons hitting the sensor. Measuring a target that is both cosmologically distant and heavily filtered will push the instrument's sensitivity to the absolute limit. Future observation proposals aim to measure the specific thermodynamic split between the torus and the polar outflows in these extreme targets. If the resolved infrared signal remains tightly bound to the accretion center, it proves the feeding ring dominates the thermal output universally, no matter how aggressively the black hole consumes matter. But if the signal bleeds outward into massive expulsion cones, it will confirm that the old exhaust models weren't completely wrong. They simply required a much larger cosmic engine to trigger. There is a real scientific risk that the blinding glare of a quasar will completely overwhelm the interference pattern, resulting in unreadable data. If Webb cannot piece together that extreme luminosity, the burden of mapping quasar cores will fall to next-generation ground-based observatories.
The extremely large telescope, scheduled to come online in the late 2020s, will utilize a massive 39-meter primary mirror, potentially providing the raw optical power required to finish the map. Regardless of which observatory eventually captures that definitive image, the baseline methodology of studying active galactic nuclei has fundamentally shifted. We no longer have to settle for blending starlight into blurry optical smears and relying on mathematical assumptions to guess how a black hole behaves. The January 2026 Circinus paper demonstrated that high-contrast space interferometry is a viable reality. We finally possess the structural mapping tools necessary to cleanly separate a black hole's accretion zone from its expulsion zones. We just have to wait for those tools to stare directly into the brightest fires in the cosmos. Will the universe's most violent eaters ultimately prove to be messy spitters? Or does the compact feeding ring always dictate a galaxy's fate? If you want to follow this exact observation and see the data the moment it drops, make sure you are subscribed to Quasar Quest.
Let us know in the comments which cosmic mystery you want us to investigate next.